Is there any energy imbalance at the top of atmosphere? According to the greenhouse effect hypothesis, the answer must be yes. Otherwise, the global warming due to increasing CO2 in the atmosphere can hardly be justified. But has any imbalance been instrumentally observed at the top of atmosphere? Welcome to Yun Tuition. I am Yun. Let's continue discussing basic issues in weather and climate research. Today, I'm going to report what I have found recently in line with John Clauser's recent lecture on the measurements of the imbalance, or Earth's energy imbalance for short. Are you ready? Let's go and have fun. John Clauser is a great experimental physicist whose expertise is in accurately determining the amplitude and phase of electromagnetic wave or photons, often called radiation by climate researchers who wish to understand the fundamental issues in climate theory.
The things that my dad did that helped me along was taught me to be skeptical of everything. Interpretations of experiments. Go back and look at the original data, if you possibly can.
In 1972, for the first time, his critical measurements of photons confirmed that Albert Einstein, his hero, is wrong about quantum mechanics. Despite all the rejections and mocks around him when his adventure began, including Richard Feynman.
Everybody knows predictions of quantum mechanics are perfect. Don't even need to look. Dismissed me immediately.
Earlier this year, at the age of 81, John Clauser pointed his finger to Graham Stevens, a high-profile climate researcher who knew relative transfer equation and Malavi's work as early as 1981 in Melbourne. Here is the key papers in question, published by Stevens et al. In 2012. In their figure 1, they claim that the Earth's energy imbalance, or EEI for short, observable at the top of atmosphere is 0.6 plus minus 0.4 in watt-meter square, inferior from their estimated imbalance at the surface, 0.6 plus minus 17 in watt-meter square. Notice the uncertainty are 0.4 and 17 watt-meter square, respectively. By the way, the pink lady, Sabina Hausenfeld, only shown the upper half of this figure to her audiences. Klaus first remarked that such a small power flow imbalance can hardly be measured given a number of fluctuations arising from random variation of the clouds and thermal processes near the surface. In particular, John Clauser used two early papers as examples. One is by Stevens et al. In 1981, another by Ramanathan in 1987, respectively. Their results, as you can see, for the imbalance were quite different. One is 6.9 watt per meter square for warming. Another is -3 watt per meter square for cooling. As pointed out by Clauser, their estimates were considered as do not meet quantity standards in the 2003 US National Academy and Research Council report. Further, Clauser explained to his audiences that the uncertainty in obtaining the imbalance at the top of atmosphere is too large to derive a non-zero imbalance. In doing so, he used this basic equation for uncertainty propagation for uncorrelated measurements. It is simply shown the uncertainty for the imbalance should be larger than any of the three uncertainties in measuring the incoming solar radiation, ISR, reflected solar radiation, RSR, and outgoing non-wave radiation, OLR. Using the same data Stevens used, Klaus noticed that their calculation for the imbalance at top of atmosphere should be 0.5 plus minus 3.9 watt per meter square, rather than 0.6 plus minus 0.4 watt per meter square. In other words, the uncertainty should be 10 times larger. In fact, Stevens recently admitted that.
Our uncertainty overall in terms of the sum of all of the fluxes in and out of the atmosphere and just in the broad measurements themselves is about 4 watts per meter squared.
Because the desired imbalance is about 1 watt per meter square, it seems impossible to measure the imbalance at the top of atmosphere. Indeed, this is bad news for entire community of climate research, as many climate researchers rely on this magical number to justify their models, and more importantly, making their living. Unsurprisingly, the person who jumped out to categorically define the direct satellite-based observations of the imbalance, or EEI, was James Hansen. In 2005, Hansen et al. Published this paper in which the estimated imbalance was subjectively reset as 0.85 plus minus 0.15 watt per meter square, nearly 40 times less than the original uncertainty from using instrument at the top of atmosphere. How could they do that? Simple, but weird. Both the averaged imbalance and the uncertainty were inferred from their climate modeling and reanalysis of the ocean heat content measurement. In this way, not only did they predict the future warmings, but also they simulated the evidence in support of their rhetoric. That's to say, any instrumental observation at the top of atmosphere must be first and foremost conformed with inferences from climate modeling and OHC measurement in the ocean. Following Hansen's instruction, Noble et al., not Nobster, switched their modality from their satellite radiometry data to surface measured OHC data, or the ocean heat content. In addition, they also adjusted the observational EEI, or the Earth energy imbalance, originally from the series, the instrumental measurements from satellite called Clouds and Earth Radiant Energy System, so that their adjusted imbalance become identical to the estimate by Hansen et al., 0.85 plus minus 0.1 watt per meter square. How did Stephenson react to this paradigm shift? By joining force with Noble et al., he hijacked this opportunity by loudly endorsing this irrational idea as the first author in this 2012 paper. By negotiation, they agreed the imbalance at TOA should be 0.6 plus minus 0.4 watt per meter square, which has been eventually adopted in the IPCC's AR6 report. As Stephenson wrote, this link makes it possible at least to anchor the TOA net fluxes to those changes in OHC, or the ocean heat content, and place a tighter constraint on the TOA energy balance.
Tracking of the radiation imbalance at the top of the atmosphere actually tracks the ocean heat content changes made independently within situ. So we think the precision of the atmospheric measurements is significantly better than what we quote here in terms of the overall measurement uncertainty that we can best estimate.
Really? If deep ocean could store most of the accumulated energy due to the imbalance, how much is energy available for the global surface warming? In 2021, Noble et al., not Nobsters, published another paper to further consolidate their inferential argument without further measured data. We adjust the satellite EEI measurement to the ocean in situ values by applying the offset to the satellite measured Earth energy imbalance. What a joke. If one could adjust the observed result in agreement with his or her theory, then that theory must be a hoax. Who said that? That is the background and self-confession of how Stevens et al. Were caught red-handed by John Clauser earlier this year. In summary, we are fortunate to have Dr. John Clauser, who can shed new light into this fundamental but obscure issue at the very core of climate research, namely whether or not the imagined imbalance can be directly measured. How about Stevens now? In his recent reply to Sabine Hausenfeld, he didn't say any single word about the fabricated imbalance. Perhaps he is too old to remember what he had done.
The observations that I'm going to sort of report on is from the series EBAF. EBAF is the energy, something it's called balance and field energy. I think it's energy balance and field fields or something like that. I'm trying to find the acronym.
Go back and look at the original data, if you possibly can. What was really done, and be skeptical that they have drawn the right conclusions.
Thank you for watching. Thank you for donation. See you next time.